Okay, this is a tutorial on electron configurations. We're going to go through configurations, the filling of the orbitals. So if you haven't had a lesson on orbitals, if you're not acquainted with what orbitals are, you should certainly look at the orbitals tutorial first. Okay, so this is a tutorial on the fundamentals of electron configurations as well as how they relate to the structure of the periodic table. So first let's take a look at the basic rules of how electrons fill orbitals. So this is a nice schematic showing on the y-axis increasing energy and the orbitals shown as circles as increasing in energy as we go up in the order of filling orbitals. So let's take a look at how electrons fill the orbitals, in other words going from lower atomic number elements to higher atomic number elements. So if we start out at hydrogen, one of the rules is orbitals are filled at the lowest available energy levels. So hydrogen would fill the 1s orbital with its 1 electron. And in terms of writing out electron configurations, we would show that hydrogen has that 1 electron in 1s by writing 1s and then a superscript 1 to show that there's 1 electron in 1s. Let's take a look at helium. Helium comes along and fills 1s with a second electron, and so we would say that the 1s orbital has 2 electrons. And that's the maximum amount of electrons that we can put in any one orbital, so that's a second rule. The most amount of electrons that can go in any one orbital is 2 electrons. Let's take a look at carbon. Carbon has 6 electrons, and our first rule being that electrons fill lowest energy levels first, so we have 2 in 1s, and then another 2 in 2s, and then we need 2 more, but we're not going to double up in 2p because electrons fill orbitals individually that are at the same energy level before they start pairing up. So carbon would have in 1s 2 electrons, in 2s 2 electrons, and in 2p also 2 electrons. And that's shown right here, drawn on the schematic. So let's look at those rules that we've been talking about. So the first one is called the Aufbau principle. Electrons fill lowest available energy orbitals. And then there's the Pauli exclusion principle, no more than 2 electrons per orbital. And then finally, Hund's rule, electrons fill orbitals of equal energy before pairing. So as we look at a few different elements and their electron configurations, in other words, the arrangement that the electrons are in the atom, we will be using each one of these rules. So let's keep going with some elements that have more electrons. For example, let's look at oxygen. So oxygen has a total of 8 electrons, and we already have 6 shown here. So the 7th one would go in the empty orbital in 2p, and then finally now we can start pairing up since all the 2p orbitals have 1 electron. So in 1s there's 2 electrons, 2s there's 2 electrons, 2p there's now 4 electrons. So these are the electron configurations so far of helium, hydrogen, carbon, and oxygen. So all you're doing is writing the sublevel. These are the sublevels. And then with superscripts showing how many electrons are in each sublevel. So for oxygen, we've got 2 electrons in 1s. In 2s, there's 2 electrons. And in 2p, there's 4 electrons. Let's take a look at something a little bit more complex. How about cobalt, number 27? That means a neutral cobalt atom will have 27 electrons. Well, let's add the rest of the electrons until we get to 27. So we've got 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So cobalt would be 1s2, 2s2, we've got 6 in 2p, so 2p6, 3s2, 3p6, 4s2, and then finally 3d7. So this would be the electron configuration of cobalt. And if you added up every superscript, they would all add up to 27 electrons. So as you might see, there is an order to the filling of the sublevels, and the order is you keep on going to the next higher energy level orbital. So a good mnemonic device for remembering the order that the orbitals are filled, the sublevels, is to simply write them out in a very specific way that I'm going to show you here, and it's an easy way to remember the order. To create a table of the orbitals, which I will draw out here, and it's actually pretty easy to remember. In a column, write out the s orbitals, so 1s, 2s up to 7, 3s, 4s, 5s, 6s, and 7s. And then you start with p. In another column, 2p, 3p, 4p, 5p, 6p, 7p. And then another column, the d's, starting with 3d, 4d, 5d, and 6d. There's no 7d. And then finally the f's. There's only 4f and 5f. So what you can do with this layout is draw diagonal arrows from top right to bottom left, and that gives you the order of the filling of the orbitals. So the first is 1s, 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. We have now filled every orbital available for all the elements on the periodic table. Okay, so as you can imagine, when we get to many, many electrons, things are going to start to get a little awkward when you're writing so many electrons. And there is a shortcut, there's an abbreviated way of writing the electron configurations, which we'll look at right now. So in this worksheet, we have just all the elements going down, hydrogen onward, and so we just put an arrow and just represent an electron. That would be, in 1s, there would be one electron. As we were just talking about, what happens when things complicated, when we run into too many electrons. So let's take a look first at neon. So neon is 10 electrons, it's atomic number 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so neon is 1s2, 2s2, 2p6. So that's a noble gas. And noble gases always have their outermost s and p electrons filled, s2p6. And so we take noble gases as the abbreviated form. So let's take a look at the next one. Sodium, Na. It has one more electron than neon does. But the first 10 electrons have the same configuration that neon has. So we can just write neon in brackets to show this configuration, and then simply write whatever comes after that. In this case, 3s has one electron. So sodium would be neon 3s1. Let's skip down to 14, silicon. Again, every orbital is filled the same as neon plus 4 more. So there'd be 2 and 3s, and then another 2 and 3p. So silicon would be neon in brackets plus 2 electrons in 3s and another 2 electrons in 3p. So silicon is neon 3s2, 3p2. Let's see what happens when we get to argon. Argon is 18. All of the 10 electrons that neon has in the same configuration, plus another 8 more. 1, 2, 3, 4, 5, 6, 7, 8. And so argon would be neon 3s2, 3p6. Notice that we've reached a noble gas again. We're at s2p6. So for the next one, we can start using argon as an abbreviation. So for number 19, potassium. So now every one of the orbitals that argon fills is filled with electrons, plus one more, left the box out, and so therefore we have argon now as an abbreviation plus whatever comes after that, in this case one electron in the 4s orbital. And if we look at calcium, the next one, we've got argon 4s2. Notice that if we wrote it all out, we would have argon there plus 4s2, and that's exactly what we've written right there. So using noble gases is a nice way to abbreviate electron configurations and not having to write out very, very long electron configurations. Let's take a look at a really fast way of how to look on the periodic table, how to use the periodic table as a way to get a quick electron configuration. So the modern periodic table is organized very specifically with the order of electron filling. So let's see how that works. I think if we first look at how the f orbitals fit into the table, this is what the table would look like with the f orbitals in the table. So we can split the table up into different blocks according to where the last electrons are going. All the elements right there have the last electrons going in the s orbital. All the electrons in the f block have the last electrons going in f orbitals. All the elements in the d block have their last electrons going in d orbitals. And finally, all the elements in the p block have their electrons going into p orbitals. So how can we use that organization to figure out electron configurations? So here's the extended periodic table with each period split into the different energy levels that each sublevel is in. But let's go back and look at a regular looking periodic table where the f elements are not in it, which is what you normally will be looking at. So the outer electrons are given by the number of the period. As you go across from one element to another, you just keep on adding one more electron. And where is that electron going? That is given by the sublevels shown here. And the order simply goes, all of these elements have their last electron going in 1s, so they're all going to end in s1, they're outer electrons. These, we've added one more to s, so they're all going to end in s2. And these are all going to end in D1, D2, etc. We've got all the way up to D10. And then finally in the p block, we start filling the p orbitals. So all of those elements, their outer electrons will be p1, p2, etc. Here we've got up to p6. Those are the noble gases except for helium, which doesn't have any p electrons. It just puts its second electron in 1s. So let's just pick a random element, for example that one right there. We don't even need to look at the periodic table if you understand the organization of the table to know what electron configuration it will have. It's going to end in p5, and the period that it's in tells us which p it's going to be. 2p. So it's going to end in 2p5, and everything that comes before it is going to be also filled. So we're going to have 2 in 1s, 2 in 2s, and then finally 5 in 2p. So this is the configuration of this element, whatever it is, and it happens to be fluorine. Let's look at something a little more complicated. So here we're going to be going across the d elements. And we're in the p2 column. We're in period number 4. So we're going to fill up all of the orbitals up to 4p2. So let's do that. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then finally 4p2. Now let's take a look to see if we could have abbreviated that. This is the electron configuration of argon. And so what we could have done was simply argon 4s2 3d10 4p2. So to avoid this altogether, by looking at the periodic table, we're at this element right here. Just simply look at the noble gas that comes before it, argon, and that's going to be the noble gas used in the abbreviation. And then all you're doing is filling in across the next period until you get to the element you want. So let's try that again with picking an element. We don't even know what it is. We've got D10 there, D9, D8. So we know it's going to end in 4D8. What is the noble gas that comes in the period before that? That would be krypton. And so we would write krypton plus everything that leads up to that box. So let's do that. We've got krypton, and then we're just going to go across 5s2, and then 4d we've got 8. And that just happens to be palladium PD. So once you understand the arrangement of the periodic table and how the blocks are, so the S block is here, the D block is here, the P block is here, the F block is here, we have the helium exception, and if you just simply look at the number of the period, that tells you where you're going with your electron configurations, keeping in mind that all the D periods are going to be one less than the period row, and that the F periods will be two less than the row that it's in.